And thank you very much for the invitation to give this seminar. It's very exciting. And I'm Agneta Fransson, as you heard, and I'm a chemical oceanographer and senior scientist at the Norwegian Polar Institute and adjunct professor at the University Center in Svalbard in Norway. And I'm been working with research in polar oceans, both Arctic and Antarctica, for more than 20 years. And also the recent 10 years, I also start to study the Svalbard fjords. And I'm interested in looking at interactions between sea ice and ocean and atmosphere, and also the land, ocean, glacier ice and ocean and air interaction. So today I will talk about the glacial water, if it matters, or that it matters for the seawater and sea ice carbonate chemistry, CO2 fluxes and ocean acidification in Svalbard fjords. And the outline of the talk is to give first a background of Svalbard fjords and glaciers, and Tempelfjorden and Kongsfjorden will be the focus on this talk. And I will give a short introduction to the marine carbonate chemistry and the importance of carbonate ions. I will show some methods and variables that we use, and effects. Then I will show effects of glacial water and if glacial water really matters. Then I will show some results on seawater and sea ice processes, and also the effect of glacial water. And then I will give Svalbard fjords, I will put Svalbard fjords in a larger Arctic content and climate change, and I will wrap up with a summary and some short showing them some ongoing projects and collaboration. So first I will just show you on the map where we are right now. In this talk we are on Svalbard, and it's north of Scandinavia. And the fjords I'm going to present is the Tempelfjorden and Kongsfjorden, and they are located on the western side, the west coast of Svalbard. And Tempelfjorden is located at 78 degrees north, and Kongsfjorden is located at 79 degrees north, about. And they are surrounded by glaciers. I will look into these different fjords, focus a little bit on how these studies have been done, and how the fjords looks like in these schematic maps. And the Tempelfjorden to the left-hand side here is a 40-kilometer long fjord, and it has no pronounced sill. But in the inner parts of the fjord, there are three main glaciers, which is Tunabren, Bogebren, and von Postbren. And Tunabren is tidewater glacier, while the other two are land-terminating glaciers. And there is also sea ice in the fjord in winter. Sometimes it varies a lot. Sometimes it's the ice set, for example, in 2012, it's here in the middle, and then the year after it was further out in the fjord. Depends a lot on what year. And to the atmospheric conditions. And Kongsfjorden to the right hand side here, it's a 20-kilometer long fjord, and it has, in the outer part is no pronounced sill, but in the inner part of the fjord it has a shallow sill of about 20 meters depth. And it's also three main glaciers in the inner part of the fjord: Kongsbren, Kronebren, and Kongsvegen. And the Kongsbren and Kronebren, they are tidewater glaciers. So I will show some more results on these studies, and some sea ice in the landfast sea ice also in the inner part of the fjord, which also varies a lot between years. On this map, I will just show a brief introduction to some currents outside on the west coast of Svalbard. You have the red arrows, warm Atlantic water, and it's also a cold current from the east of Svalbard. It's traveling along the coast, and these two currents, they sometimes mix, and they also entered the fjords on the west coast and affects the conditions there. At present, about 68% of the glaciated area of Svalbard drains through tidewater glaciers that have a total terminus width of about 740 kilometers. And on this map, the blue fields are tidewater glaciers. And the red arrow is the Kongsfjorden. So we have a large area of tidewater glaciers here, and also the calving front of about 30-40 kilometer width. And the yellow arrow is the Tempelfjorden. You have a little bit less of tidewater glaciers, and you have also less of the calving front width. But these glaciers, for example, in the Kronebreen and Kongsvegen and Kongsbjörn, they have retreated. And this, of course, will also result in loss of runoff of water. And the tidewater glacier annually contribute 1 square cubic kilometer of meltwater in Kongsfjorden, and Kronebreen and Kongsvegen alone discharge 2.5 million tons of suspended sediments during the melt season. And that is usually in summer, where you have lots of variability in these sediment plumes here. See on the figures on the map, on the photographs here. See these brown sediment plumes. And continuing with Kronebreen and Kongsvegen, that they have retreated, and this year scale from 1860 with the blue lines and going to now to 2010 or so, the yellow, it has retreating in a large area here for both glaciers. And if we look at the photographs, the bottom, the black and white photograph from 1939 is taken from the Zeppelin Mountain, and you look towards the Kronebreen, and you see if you compare to 2009, which is taken at the same spot, you can see the retreat that the glacier has moved in, and loss of ice has disappeared. And this is some interesting feature. That is the Blomstrandhalvøya. It's a peninsula in 1936. As you see in this black and white photograph here. But in 1990, we saw this only bridge of glacier ice. And suddenly in 2009, this bridge of glacier was gone. So the Blomstrandhalvøya, the peninsula wasn't a peninsula. It is an island. And the landmass sea ice has decreased as well. And that will also, of course, have effect on glacier front, destabilizing effects on the glacier fronts. And if you look at the diagram here with from 1967 to 2016, where the black illustrates the monthly sea ice area anomalies for the Arctic. The black is Svalbard, and the blue is Arctic sea ice extent. And the red is a trend for the Svalbard sea ice extent during this period, and this is a decreasing trend. And sea ice formation is also important in autumn and winter, which also contribute to circulation and vertical mixing of the fjord when you have this brine from the sea ice and dense water, and it causes this mixing. So we continue to look at the fjord circulation and what's happening in the fjord with the water masses. And you usually have 3 layers in these fjords, and it's a surface layer, intermediate, and bottom layer. And the red arrow here at the bottom is Atlantic water inflow. This is a warm, salty water entering the fjord, and it goes in across the sill, if it's possible, and it melts off the base of the glacier, and this fresher water here will mix with the salty water and get lighter and rise to the surface, and it will take suspended material and particles to the surface. And you also have meltwater from the surface, from the glacier, and you have this mixed water also flowing out of the fjord. And this is general circulation, and that also depends on wind and pressure gradients in the fjord. So we have studied the seasonal variability, but we also have annual cruises and fieldwork to study the carbonate chemistry in Kongsfjorden and Tempelfjorden since 2011 within the Norwegian Center Ocean Acidification flagship. And we use the fjords as climate labs. Because it's convenient. You have, because you can have, it's a small area, you can get information on possible effects of climate change. And if you also, as I will show you later, we have also contrasting years with cold and warm years. And that will also give varying Atlantic water inflow and effects on the freshwater and glacier input, and effects on ocean carbonate chemistry and carbon cycling. So the figure here just shows two different scenarios. If you have a cold water entering the fjord, or if you have a warm Atlantic water entering the fjord, you will have, with a warmer Atlantic water, you will have more glacier melting at the base of the glacier. So that will have effects on different processes that we'll come back to as well. So I also studied maps of bedrocks in the Svalbard area. Here is an old map to left-hand side by Hoel and Holtedal from 1912. So it shows this geological map of Svalbard, and the blue area here is the carbon, and that is in both Kongsfjorden and in Tempelfjorden. And in the other figure here is a reconstruction of the Svalbard sedimentary basin, and it's from 300 million years ago, about 300 million years ago, when it was formed, this carbonate bedrock from the marine limestone and from both deep and shallow limestone. So Svalbard rock types, not in all area, but in this area, it has a bedrock that includes limestone and dolostone, silicified limestone, and also sandstone. And this is the bedrock of carbonate is really efficient, and I will show how that will affect the fjord water in the sea ice, and how it also has the potential to affect the buffering capacity in the fjord. So carbonate ions are important, and I will show that. Glacier water matters for the carbonate chemistry in Svalbard fjords, and in this figure here from Hopwood et al. In 2020, it shows different processes in the fjord that affects the carbonate chemistry. So I will go through some of these processes and see how the glacier water matters for the carbonate chemistry. So first I will introduce you to the marine carbonate system, which is a buffering system, and that means that it buffers against acidic compounds such as carbon dioxide. And it consists of several species: the carbon dioxide, carbonic acid, bicarbonate, and carbonate. So I have this acid on the left-hand side and the base on the right-hand side. And depending on if it's CO2 going into the ocean, or if it's going out from the ocean, or if we have different processes that affect carbon dioxide, these compounds will go in different directions to compensate, to balance each other in these chemical reactions. So most of the compounds consist of the bicarbonate, which is the main species when you have a pH of about 8 in seawater. And this buffering system also depends on temperature and salinity, and with cold and low salinity water, you increase the CO2 solubility. So that is the case in the Svalbard fjord and in the Arctic Ocean. So if we have a lot of, if we have CO2 from the atmosphere that is absorbed by the ocean, the buffering system will, first the CO2 will react with water to produce this carbonic acid, which is a weak acid, but it will push the reaction towards the bicarbonate, which is 90% of this species. And on the other hand, which is the carbonate, you have a strong base, and that will react with the hydrogen ion to produce bicarbonate. So the reactions will go in both directions towards the bicarbonate, and that's the main how it works. This is the main construction of this, or how it works, the function of the buffering system. So in total CO2 and carbonate with water, it will produce bicarbonate. And this also illustrates the carbonate chemistry, and it is the balance between the carbonate, CO2 and carbonate ions. And it's the pH that determines the proportions between the species, but also the species that determines or controls the pH. So it's like the hen and the egg a little bit. As I said, pH in the ocean is about 8, but it can vary between 7.5 and 8.5 depending on different processes or more short-term processes. But also with ocean acidification, this pH has actually decreased and have this more has on a longer time scale, which hasn't recovered because it's also a slow process. So at 8, you have carbonate and CO2 in different proportions. And when you increase CO2, you will decrease carbonate ion. So you will also have a lower pH here, the red line here. So when CO2 increases, CO2 decreases and pH decreases. That's the main or simple explanation of the carbonate chemistry. It's good to understand this species, and especially the carbonate ion is very important. So yeah. So seawater total alkalinity is a measure of the buffer capacity and the acid base in the pH changes. And alkalinity is defined as the excess base in seawater or the sum of excess proton acceptors, and that is the negatively charged ions. And if you look at this cloud here, you see already know the carbonate ion and the bicarbonate ion, and these are negatively charged, so they can take these hydrogen ions. And you have also lots of other negatively charged ions in seawater that also can react and buffer the system. But the bicarbonate and carbonate are the main and the largest buffering species. And we can actually measure the alkalinity. As I said, it consists of the bicarbonate and the carbonate, and also borohydroxide and hydroxide and all these others, which are minor, but they can also are calculated. So the salt in organic carbon also we can also measure, and that also consists of bicarbonate carbonate, and also CO2. So they are slightly different, and these two variables are very important when you look into pH and how that changed, and the carbonate chemistry. So how we work to get the knowledge about the carbonate chemistry is to sample water, and this is winter in Kongsfjorden, and we have a water sampler. Sometimes we go out with small boats to take water in these Niskin bottles, and sometimes we also take water samples from the sea ice in a hole. And we also sample in summer. We go with small boats, or we go with a larger research vessel. This is a Kronpris Håkon, the Norwegian, relatively new research vessel, ice-breaking vessel. And then you have a row set with several of these Niskin bottles. You can have water sampled at different depths. We also sample for sea ice, and we drill these ice cores using the corer, and we cut the ice cores in pieces and we melt them, and then we analyze them with regard to different chemical substances like carbonate, all in carbonate chemistry, pH, and nutrients, and isotopes, and salinity. And temperature is of course important. Sometimes we use snowmobiles to go out in Tempelfjorden, for example, and sometimes it has been really bad weather, so we have to turn and go back to Longyearbyen again. We work in the lab, so we analyze the carbonate chemistry, pH, dissolved in organic carbon that I showed you, and the total alkalinity, which are very important for the carbonate chemistry, and we also analyze PCO2, and then we can calculate carbonate and bicarbonate. And this presentation is based on some field studies and results from papers from Tempelfjorden and two from Kongsfjorden, and I will show results mainly from the latest paper in Annals of Glaciology from this year, and it's about the influence of glacial water and carbonate minerals on wintertime sea ice biochemistry in the fjords. So I will show some results on that soon. So first, glacial meltwater matters for seawater chemical ions. The blue circle here in the figure, it shows the meltwater from the glacier, and if it's from the surface, it's really fresh, and if it's from the surface glacial meltwater, then it can also contain other sediment particles. But the glacial water with the freshening effects, it has also dilution of ion effect, and that will of course dilute all the carbonates and the bicarbonate ions as well. And that could lead to increased ocean acidification. So water column stratification is also an effect of this surface meltwater, which I will talk a little bit about more later. The total alkalinity, buffering capacity, and calcium carbonate saturation decrease with increasing amount of fresh water. And these figures illustrate how the total alkalinity on the y-axis and the freshwater fraction, and how that total alkalinity decrease with increased freshwater fraction. And that's for the whole year, when from January to September, we have this decrease in alkalinity with the freshwater fraction. The other one to the right-hand side shows this saturation, calcium carbon saturation, which is a measure of how much free carbonate ions there are in the water. And if this value is below 1, it means that the calcium carbonate will chemically dissolve. And for some organisms, this is very critical because that will have damage on their shell, and they have problems to produce new shell. Some organisms, for example, the butterfly snail, which is in the figure here or the photograph, it has a problem to calcify between 1 and 1.4. And this has also seemed to be, has a decreasing concentration of this aragonite saturation with increase in fresh water. So that could be critical for some organisms. But it's not only fresh water that has a large impact in the fjord on the water and sea ice. It's also the biological consumption, and that has a competing effect. And especially in summer, when you have very large, you have a large contribution to primary production, especially in spring. And when you have the primary production, you consume CO2, and that leads to increasing carbonate ions. So these are competing and have contrasting effects, and very important in spring and summer. And winter has, it's not so pronounced, but it's usually more CO2 and less fresh water and no primary production. So we studied the winter and summer conditions in Tempelfjorden near the glacier front, and we have studied contrasting years to illustrate how different it can be and how it varies. So the contrasting years from a warmer year in winter 2012, we had a less and thinner sea ice, and it was formed later in the season. We had more glacier water and precipitation. And if we look at the ice maps, conditioning in January, it was open, the blue here, and it started to form open drift ice in February, the yellow, and then it started to form a little bit more of closed drift ice, and then very open drift ice in April. But for the colder year in winter 2013, it was more and thicker sea ice, and there were less glacier water and more Atlantic water and Halland convection with this mixing due to ice formation and sea ice brine. So if you look at this preconditioning in January, with the blue is open water in January, same as in 2012, but it was really cold and started to freeze, and it was closed drift ice in February and very close drift ice in the inner part of the fjord, and it's formed fast ice in March, which continued until April 2013. So the glacier water effects on sea ice, I will show you soon how that looks like. We use stable oxygen isotopic erasers to trace sources of water and mixing. So we use these M members of seawater, sea ice, and meteoric water. For glacier ice, we use -16 of oxygenating, and for seawater around 0. And then we have sea ice, which is a mixture of glacier ice and sometimes sea ice. So that you have mixing lines between the different N members here. So the negative oxygen-19 indicates mostly meteoric water, precipitation, glacier, meltwater, or river runoff. And we need to distinguish glacier meltwater from snow, rain, or river inputs. But in Tempelfjorden, we don't have so much river inputs in the inner parts of the fjord. So we will just distinguish snow, rain from glacier water, and that we could investigate using silicate concentration, and that has been used in other previous works as well. So here are the sea ice variables for April 2012 and April 2013, and this is show the black is seawater. So that's a border between the water and ice. So this is sea ice, and in the inner part of the fjord with the glacier front, you have the thicker ice, and it is thinning towards the ice edge. And in 2012, the ice was thinner compared to 2013, and you have, it was also warmer ice in 2012, the red, yellow, and it was also less salinity with this blue compared to this light blue and yellow in 2013, and you have also negative values of O18, this blue here, which is not observed in the 2013, where we have this mixed layer, really mixed. This is sea ice, so it's mixed in the, or it only consists probably only on seawater. But that's something we will have to look into. We also have freshwater fraction, which was higher in 2012 in the inner part of the fjord, which we couldn't see in 2013 to the same extent. So, we concluded that we have this meteoric water in the inner parts of the fjord in the 2012, which was not observed in 2013. And the sea ice silicate were highest at the glacier front in 2012, and that coincided with high freshwater or fresh meltwater and low salinity and low oxygenating. And that suggests the influence of glacier water and not precipitation. We also have low alkalinity and DSE because of the dilution. Here you see the silicate, which was really high in the inner part of the fjord in 2012, which was not observed in the 2013 and not in any place in the fjord. So we measured, we could estimate the amount of glacier water in the sea ice near the glacier front in 2012, when we used the formulation of fresh meltwater using n members of oxygen-18 in ice, in seawater, and in glacier meltwater. And the highest integrated freshwater fraction of 54% in April was found at the glacier front. This red here is station 1, is the inner part of the fjord, and it decreasing towards the ice edge is red, is 2012, and the black is 2013, which we have much less of meltwater. And at each station and each depth, it also showed that 60% was found in bottom ice in March, April 2012 at the glacier front, and it was nearly 5 times higher than found at any other station, and also higher than the 2013, which was these black lines here. We couldn't see a lot fresh water. So we now wonder if the carbonate ions, the CS, are added with the glacier water, because we could analyze or estimate the carbonate and bicarbonate concentrations that they were elevated in 2012 in relation to salinity, and that might be addition of mineral or excess of carbonate. And it's quite we plotted the bicarbonate and the carbonate against oxygen-19, and with the dilution line from glacier water -16 to seawater at about 100 for carbonate and 2000 for bicarbonate. We found this above dilution line was excess of carbonate ions and bicarbonate ions, these red dots in the ice in 2012. And we have also these black crosses, which are ice in 2013, and with a positive O18, that means that it's seawater source, and the negative O18 is the glacier water. So we conclude that this is mainly from the glacier water in the ice 2012. But can these ions be derived from the sediment, bedrock, or sea ice? So we have to find out where these excess carbonate ions come from, which we find in the ice. glacial meltwater adds particles to the seawater, as I also showed you earlier, because this figure you see from the bedrock, you have these sediment plumes from the bottom of the glacier and also near the bottom of the fjord, which enters the surface with this plume from fresher water to the surface, and this sediment will contribute with the carbonate ions and particles. But this sediment will also contribute with iron, silicate, ammonia, and trace metals, and that is a large importance for primary production or photosynthesis. That will also be something I will show soon. But also the sediment plumes, they also, if it's a lot of sediment, they also limit light, which also have negative effect on the primary production. So this plume is from the Kongsfjorden, and Ny-Ålesund is right here. So from the glacial front and out, the plumes is reached far out in the fjord, and even outside the fjord onto the shelf and shelf slope. And we have also the sediments from this plume in our samples here. And when we analyzed the total alkalinity, we found that when we plotted them, alkalinity on the y-axis and the salinity on the x-axis, with this ratio, we found that we had at the intercept of 0, where we assumed the fresh water, we had an intercept of 1142 micromole per kilogram in 2012, and that means that it's not fresh, really only fresh water. It's also something else that adds alkalinity to this water, to this sample. And in 2013, we didn't have this high intercept of 0 salinity. We have 526, so we have a little bit less N member of this fresh water. So, but some contribution for something else, because if you have no contribution of any particles or carbonates, then it would be 0 with only fresh water or dilution. So we found in the sample, we found calcite and dolomite carbonate minerals from bedrock, in the sea ice sample, the snow and glacier ice. And these shows figures from the calcite to the left-hand side and dolomite to the right-hand side. And this is analyzed, or this photos taken by Raman microscopy by Janot Nerke at AVI. So we have minerals from the bedrock. And in the carbonate chemistry, the chemical reactions of calcium carbonate and metals are very important, and it can produce and dissolve with these carbonate metals or metal carbonates. We see the metal and the carbonate will produce a solid metal carbonates, but could also go in the other directions, so it will dissolve. And if we look at the reaction for dolomite dissolution, it reacts with water and carbon dioxide, and it will produce bicarbonate ions, 4 bicarbonate ions. And calcite and icate when that will dissolve with water and carbon dioxide, it will produce 2 bicarbonates. So if we go back to the figure where I show the excess bicarbonate with the red dots in this glacier water and excess bicarbonate from the ice 2012, we can conclude that this is from the bedrock minerals, especially from the dolomite dissolution, this higher concentrations. And icate, I also mentioned, that is formed in sea ice by chemical physical processes, and it can also form and dissolve. And that has excess alkalinity that is left in the sea ice, and it dissolves in the surface water during ice melt, and it contributes with carbonate ions and alkalinity, and increase the potential for CO2 uptake. So these photographs are these ichorite crystals that you find which are formed in sea ice, and they contain calcium carbonate. And this is these crystals are made from artificial sea ice, so they are a very nice shape of these crystals. So we also found in this newly formed sea ice in Kongsfjorden, very thin ice, and we found in these frost flowers, we also found high concentrations of alkalinity, but also high salinity and other chemical compounds, also halocarbons. And we found that also ichorite in these frost flowers. And at the same time, we also saw this release of CO2, or we could estimate the release of CO2 from the frost flower, and also release of other gases as well. So I showed this figure with a similar figure with alkalinity and salinity ratio, with excess alkalinity against salinity in this with the red dots here in the ice 2012, when you have the negative O18, where you have the glacial water. And when it's above 100, we assume it's from dolomite, bedrock-derived dolomite. And where you have on the positive side of the oxygenating, in 2013, we have mainly the effects of ichorite, because that's usually lower. This alkalinity salinity ratio is less than 100, and that is found in other studies before this. And this concludes that the dolomite contributes twice as much to the buffering capacity and potential for CO2 uptake than calcite and ichorite. So now I come to the glacial effect on primary production, which also have an effect on the CO2, because it's a consumption of CO2 during primary production and photosynthesis. And primary production is dependent on stratification of the surface water, which you get from the meltwater, but also from the supply from the minerals, from the bedrock of iron and nutrients, from the sediments and from these particles. But that will favor primary production. But the sediments can also limit the light, which will decrease the primary production or limits primary production. So this will have implications for also for the carbonate ions that will increase when CO2 is consumed at photosynthesis, and with less of this primary production, we will also have less carbonate ions. So this is just a short how photosynthesis is consumed by phytoplankton, producing using nitrogen and phosphate, and producing organic carbon like sea ice, algae, or phytoplankton. And in this figure with the open water, where you have enough light for primary production, you have decrease in CO2 and the corresponding increase in carbonate ions. And if you summarize all these processes, the glacial meltwater increase the potential for ocean CO2 uptake. We all see that these processes have effects on the direct ocean CO2 uptake, and with this uptake, it also increases ocean acidification. And the Arctic fjords are vulnerable to climate change and to this increased uptake of atmospheric CO2. And with the reduced carbonate ions, you will have reduced calcification and the dissolution of shells. But with the reduced pH, you will also have changes or effects on the ion transport in the organisms, in the marine organisms, and enzyme activity, protein function, and chemical reactions, and also the distribution of micronutrients, such as iron, which are important for organisms. And we use this calcium carbonate saturation, which I already introduced, and is free when the free ions are less than the saturated it's less than 1, means that it's undersaturated, and it dissolves calcareous shells. And when it's more than 1, it's supersaturated. The competing effects of glacial water, the larger processes of glacial water effect, and the photosynthetic CO2 consumptions are competing. They will decide how much ocean CO2 uptake and ocean acidification we will see in the Arctic fjords, and also with the sediment loads and stratification. That will of course have effects of all these processes that I've been talking about, and also the minerals from the bedrock with the carbonate, and that of course depends on the fjord and the bedrock surrounding the fjord, and that will also affect the whole ocean circulation, depending on the fresh water and how that will continue in the future. So I will put Svalbard fjords in a larger Arctic context, and there are several Arctic fjords that are affected by increased glacier water discharge, not only in Svalbard, but also in Greenland. We have several fjords that have this freshwater discharge, and this is from Hopwood and colleagues 2020. And they also found, Cantoni et al. has found that glacier drivers of marine biochemistry indicate a future shift to more corrosive conditions in an Arctic fjord. And with corrosive, this means the more fresh water that will dilute the carbonate, and it will also decrease the saturation states for and the carbonate ions for buffering the ocean acidification, but also for forming calcium carbonate shells. So this calcium carbonate undersaturation has already been observed many years ago in the Arctic under the ice in freshwater influenced shells. This was from 2005, where we found this low aragonite saturation of below 1 already on the freshwater where we have ice melt, river runoff, and this of course also is valid for the glacial water. And this is earlier than predicted by models where they predict this happen in 2050. So this fresh water has a large impact on the ocean acidification, and with cold and fresher water and less sea ice, it will also have the potential for more CO2 uptake in the Arctic. And with changes from tidewater glaciers to land-terminating glaciers, that could also, in a warmer climate, also find that there will be less upwelling of nutrients in the land-terminating glaciers, with more sediment, limiting light, and also limiting primary production, and also very strong stratification can also limit biological CO2 uptake, because you will not get nutrients to the surface. And that will also affect the potential for ocean CO2 uptake, that will be less as well. So the circulation in the fjord to the outer shelf and coast may also change. So there are climate effects, effects of that we already observed, and here are some examples. Such warming, we already observed less sea ice and also increased meltwater, and that result in increased CO2 uptake. We also found that increased freshwater runoff increased the stratification and the increased silt and sediment load from land and glaciers that restricts light and limits primary production and CO2 drawdown near glacier fronts in Arctic fjords, but also on the Arctic shelf. We already observed low calcium carbonate ions and aragonite saturation on freshwater influenced shells, as you heard about, and spreading and shoaling of this low aragonite saturation horizons has been also observed in the Arctic due to more river runoff with organic matter, more CO2, and also thawing of permafrost that has effects on the CO2 release and ocean acidification. And this will have negative ocean acidification effects on marine organisms, especially those with calcareous shells such as the butterfly nails and shellfish. So to sum up the presentation here is that the glacial water matters for the carbonate chemistry in Svalbard fjords, and we have already seen effects on the biochemical processes and ocean CO2 uptake. And the Arctic fjords, they are sensitive to climate change, such as warming and the increased glacial water and river runoff, and that could lead to increased ocean acidification. A fresher sea ice will cause less winter time mixing of water and stronger surface stratification when sea ice melts. And that additional meltwater added from the glacier, that will cause less nutrient addition to the surface from subsurface water, hence resulting in less primary production and CO2 consumption. So this studies also show that the two contrasting winters clearly show that the amount of freshwater content in the fjord influenced the chemical and physical characteristics of sea ice and seawater, and also that the dissolution of dolomite contributes twice as much with carbonate ions than calcite and nicate to the fjord water and sea ice, indicating different buffering strengths and potential for ocean CO2 uptake. But also, of course, this freshwater has a larger effect on the ocean acidification, even if we have these minerals of carbonate ions from bedrock. But of course, for the regional characteristics in fjords due to different water masses, bedrock chemistry, glacial dynamics will decide what will happen in the future, and that will show the differences in sensitivity for CO2 uptake, ocean acidification, and effects on ecosystems. There are some ongoing projects in collaboration for time series, for sea ice, and the seawater chemistry and biogeochemical processes to study seasonal interannual variability. And we have the Ocean Acidification Flagship at the Fram High North Center for Climate and Environment in Norway, where we study the fjords and around Svalbard and in Fram Strait, started in 2011. And we have monitoring in Kongsfjorden and pelagic time series in Kongsfjorden started last year, and the Kongsfjorden Flagship, where we collaborate several scientists working in Kongsfjorden, and ICOS for the CO2 surface water. We have a legacy of Nansen. It's a Norwegian project in studying the Barents Sea and the Arctic Ocean, and the monitoring of the Norwegian Arctic waters, and also drift project of Mosaic that has been, Polarforedrag has been drifting in the Arctic Ocean with the sea ice for 1 year. So we all these projects that also contributes to the research in the Arctic. And the EVOCAL is a new project with Svalbard focus and northern Norway fjords. And the Synoptic Arctic Survey is a collaboration between several countries that will measure variables in the Arctic Ocean and collaborate on data from 2020 to 2021. And we have the Global Ocean Acidification Observing Network, Arctic Hub, which I lead. That's also contribute lots of discussion, hopefully also in the future. So we can contribute more on the discussion on the freshwater and the Svalbard fjords, and what the fate of the freshwater and effect in the Arctic Ocean, and on the climate, in continuing climate. Just want to thank contributors and funding sources, the Research Council of Norway, Fram Center, but also all the colleagues and that have contributed to the science and to samples and data and discussions. And we have also other teams that collected samples, and MPI Logistics in Longyearbyen and Ny-Ålesund, Sverdrup Station, and Ny-Ålesund Marine Lab, and also support from different ships, Lancetais, Stenkrumpish Håkon, and other. So I may have forgotten some, but I thanks everyone that has contributed to this and the continuing collaboration. And also thank you for your attention. And if you want to contact me, here is my email address. So thank you.
Thank you very much indeed, Agneta. We have some questions on the chat, but before we do that, we normally advertise the next seminar at this point. And I have to say that we've had a few changes over Christmas. It was clear that Christmas wasn't that great a time for seminars. And the next seminar is on January the 13th, and it will be by Francisco Navarro by Paco. So we have a couple missing between now and then. Francisco's been moved to the 13th, which will be the next one. But questions for Agneta. Julian, I think you're first. Do you want to unmute yourself and, or I can read it out. It says, can you see a change in the fjord's extent based on the underlying geology? Meaning since the dolomites are magnesium rich and are a bit more resistant to chemical weathering, do you see different rates of the widening of the fjords? Do you think it can be predicted for the future?
That's an interesting question, but I haven't looked into that myself because I'm not a geologist, and I just look into the particles that come out from the glaciers and the bedrock into the water and the ice, sea ice. So I really, I'm not sure. I haven't heard about that, but I mean, it could change, of course, if it depends on the exposure probably, and how much this fresher water, how much will melt and how much will be affected of the meltwater from the glacier, how much is exposed to this also subglacial bedrock, and when you have this tidewater glacier, especially when you have tidewater glacier, which you have a lot of this friction. But I'm not, I can't really answer this question of the rate, but it's very interesting. So I will see if I can find it out and can see if we can discuss this at a later stage.
Thank you. Julian said she had bad audio, so that's why she didn't do it herself. Andre, do you want to ask a question? Andre Glazowski, are you?
Oh yes, I'm here.
Thanks.
Agneta, thank you for your interesting presentation. I wonder, you mentioned that 2.5 million tons of sediments are delivered annually to Kongsfjord by glaciers. What is the ratio to the dissolved matter, or what is the amount of dissolved matter delivered by glaciers and glacier runoff or something like that? Thank you.
Yeah, you have very difficult questions to me as a marine chemist, but I haven't looked into that in detail, but hopefully there will be projects next year that we will look into both river runoff and sediment load from the rivers, also from the land, where we have lots of material. So we haven't looked into that yet. So that's something that's we hope for the next year.
Thank you.
I think we have only one more question, which is on the schedule, and it's from Paco saying, isn't there a talk by Jay Zwally? I'm afraid that Jay has just dropped out about a day ago. He sent me his title slide. I think Agneta has it as her next slide, but we won't show you. So unfortunately, Jay Zwally's talk is cancelled or postponed. We'll try and put him in later in the series. So I think there are big greetings from anyone. Is there any further questions? Have I missed any questions in the chat there? Okay, well, I think it just comes to say a big thank you to Agneta then for her talk, and absolutely fantastic slides. Really, really, really great slides there. And see you all after Christmas. So have a wonderful Christmas and New Year, and see you on the 13th for Paco's talk. So thank you very much indeed.
Thank you so much for this. That's been a pleasure to talk tonight. And yeah.
Fantastic.
So,
Happy Christmas, everyone.
Yeah, Happy Christmas and Happy New Year.
Yeah.
So I will just stop sharing here and.
Happy Christmas, and just make sure at New Year's you make sure 2020 leaves.
Yeah, stay up and make sure it goes.